The topic of my talk is Tarski numbers and different solutions to the configuration equations. My name is Akram Yousefzadeh. I'm from Iran. I work at IAU Mubarak branch. Before I start, I would like to thank SIMPA for providing me with this opportunity and for the grant. And I also would like to thank you for joining us. I will talk about Tarski numbers, configuration of groups, and amenability of discrete groups, and so on. Today, I mostly talk about amenable discrete groups, and you may be familiar with this talk, and I just want to mention some elementary topics about amenable group. So I say that a group G, a discrete group G, is amenable if it admits a finitely additive left invariant probability measure. And by this, I mean there exists a function mu from the whole power set of G to the interval 0 and 1 with the following properties. 1, the number mu assigned to G is 1. Number 2, it is finitely additive. So mu of disjoint union of subsets of G. This notation is disjoint union. A finite number of subsets of G is the sum of the numbers mu associated to AI, I from 1 to m. And it is left invariant. And by this, I mean mu of GA is mu of A itself for each G in G and for each subset A of G. The first and the easiest example of amenable groups is finite group. So it is obvious. Every finite group is amenable. If G, as a simple example, if G is amenable, if G is finite, then G is amenable. And it is because it's enough to define mu of each subset of A of G to be the cardinal number of A over the cardinal number of G. It's very easy to observe that this function is a left invariant and finitely additive probability measure. And a non-example, which is also very famous, is let G be the Free group on two generators, non-abelian Free group on two generators. As you know, we denote this by F2. This group consists of reduced boards which start with A, start with B, start with A minus 1, omega A minus 1, b minus 1 and the empty board, of course. And at the same time, you know that it can be omega A and A omega A minus 1. And at the same time, it can be omega B, B omega B minus 1. Therefore, if F2 wants to be amenable, there should be a left invariant probability measure, finitely additive probability measure from power set of F2 to the unit interval 0 and 1. And therefore, you must have mu of F2, which is 1, is equal to, by these two, this is in the a left translation of this set, and this one is the left translation of this set. Therefore, it is mu of F2 plus mu of F2 and plus mu of this set, which is not so important. So this one is 1 plus 1, and therefore you have 1 is greater than 2 or equal than 2, which is impossible. So F2 is not amenable. Okay, we have two examples of amenable groups and non-amenable groups so far. But, you know, the set of amenable groups and the set of non-amenable groups are so wide, so wider than these examples, of course. There are many characterizations for amenability of groups. I say that G is amenable if and only if I want to list some characterizations. G is amenable if and only if there exists M in L infinity of G star. I mean, positive linear functional from L infinity to C, which is positive. I mean, it is norm 1. These are equal to each other, and the norm is 1, and it is left invariant. And by left invariance, I mean M of xf is M of f for every f in infinity and for every x in G. Another characterization says that G is amenable if and only if G admits Follner condition and by this I mean for each positive epsilon and for each finite set F, there exists a finite subset K of G such that the cardinal number of x F symmetric different by, K over the cardinal number of K is less than epsilon for each x in F. This is the Follner condition. And another characterization that we will use in the next session is that the trivial representation of G is weakly contained in the left regular representation of G, and this means that for every positive epsilon and for every finite K subset of G, the supremum amount of x in K, of course, there exists a function in L2 such that xf minus f is less than epsilon f, norm to alpha. And another characterization says that G is amenable if and only if there exists a net f alpha in L1 in P1 of G. In fact, functions in L1 which are positive, non-negative, and of the norm 1, such that f alpha minus x f alpha tends to 0 in weak star topology. This condition is the weak star converging to invariance of day, and using this condition, it is proof that G is amenable if and only if for each, I say, configuration pairs EQ of G and A admits a normalized solution. Let me clean that first. This is left invariant mean. And I want to complete this. For every configuration pair, EQG of E has normalized solution. Of course, solution. Of course, I will explain it very soon. And G is amenable if and only if G is not paradoxical. And these two are the base of my talk during these 4 sessions. There is another characterization which says for each cellular automaton carrying by G and any set of alphabet, finite set of alphabet, surjectivity is equivalent to peri-injectivity. And it means that the existence of gardens of Eden patterns is equivalent to existence of mutually erasable patterns. I'm not going to explain it more because the base point of my talk, as I said, are these two conditions, and I make here this condition just to make my list as updated as I can. So let me say something else about amenability. I want to report some other theorems about amenability that I will use during my talks. It says that the first theorem, if G is amenable, and H is a subgroup of G, then G H is amenable as well. And the other one says that if G is a discrete group and N is a normal subgroup of G, then G is amenable if and only if N and G over N are amenable. Now, we can give many other examples of amenable groups and non-amenable groups. For example, let me remind some definitions. We say that G is a discrete group. G is an FC group. I will return to these groups very soon. G is FC group if for each x in G, G has only finitely many conjugates. And if G is finitely generated, it is equal to this condition that G over its center is finite. And in this case, G prime, the derivation group, is finite. Okay. So we saw that every finite group is amenable. On the other hand, every abelian group is amenable. Therefore, every FC group is amenable because the center of G is abelian and therefore is amenable, and the quotient is finite and therefore it's amenable. So by this theorem, every FC group is amenable. Every FC group is amenable. Every abelian group is amenable because of the Follner condition and other theorems. So abelian groups and finite groups are amenable, and therefore every FC group is amenable. And let me remind another definition and another class of amenable groups. I write it here, I think it's better. We say that a group G is locally finite. Yeah, let me write it complete. Locally finite. A group G is locally finite if every finitely generated subgroup of G is finite. Okay. On the other hand, there is a theorem by Day saying that if every finitely generated subgroup of G is amenable, then so is G itself. Therefore, as we see, every locally finite group is amenable. This class is another class that I will return to in next sessions. So the class of FC groups, the class of locally finite groups are amenable. And by this theorem, we can give many examples of non-amenable groups. Okay. For example, since F2 is not amenable, every group containing F2 is non-amenable. For example, if G is Z2, S star Z2, S star Z2, This is the group generated by A, B, C. These are generating set, and relation A2, B2, and C2. These elements are identity. This group is in fact non-amenable because it contains the group generated by AB and AC, and it's easily to observe that this group is isomorphic to F2. Therefore, this is a non-amenable group. And if you remove this group, one of them, then G must be amenable, of course. If G is Z2 star Z2, then G is amenable. This is nothing but the infinity. And we will talk about this one more, of course. G is the infinity, and if you find a homomorphism from the infinity to Z2, which tends elements as follow. Phi of x is 0, 1 if the length of element is even, and otherwise it is 1 when the length is odd. You know, every element of the infinity has a unique representation as this. If x is in the infinity, it is not difficult to see that x is has some presentation as this: AI, BA, BA, and so on, where I and J can be 0. So we can define the length for a member of the infinity. So this group, I write the homomorphism here, and you can see that phi is surjective, and the kernel of phi is the group generated by AB, which is cyclic and therefore abelian, and Z2 is abelian as well. Therefore, the infinity is an abelian group. The infinity is an abelian group. So just some other examples, and then we continue. Again, I want to bring some definitions. You know, I just remind this. SO3 of R is the set of all matrices in M3 times 3 such that A, it is orthogonal. It means that ATA is the identity matrix, and the determinant of A is 1. This set is nothing but the set of rotations through lines through the origin. So you can find some sigma and rho in SO3. It's not difficult. You can find it in many books. In SO3 of R, such that the group generated by sigma and rho is isomorphic to F2. And it means that SO3 is not amenable. So it's not amenable, and we explain it in group action as well. is non-amenable. Okay, and now a different class of groups are groups with the property T. So let me fill in here, except for this one, I don't need the others. We say that a group is of property T if the following happened. Whenever P is a representation, by a representation, I mean a homomorphism from G to the unitary operators on some Hilbert spaces, G to unitary operators on H, is representation if it is a homomorphism which is continuous with respect to S-rank operator topology and so on. But our group is a discrete group. Now, it's homomorphism. So we say that G has property T if whenever the trivial representation is weakly contained in this representation pi, then we can conclude that this representation admits an invariant vector. And this means that there exists a vector in H such that no elements of G can move the place of this vector. This is property T. Therefore, this corollary. If G is amenable with property T, then G has to be finite because of this condition. If G is amenable, then the trivial representation is weakly contained in L of G in the regular representation, and by property T, this representation must have an invariant vector, and in this case, it means that the constant function must be in L2, which implies that G must be finite. Therefore, the intersection between the class of amenable groups and the class of group with property T is only the class of finite groups. These are examples that explain amenability and non-amenability that we need sometimes in our sessions which are coming. So these are some elementary topics that I wanted to explain about amenability of discrete groups. Now, I said there are two characterizations for amenability that are the base of my topic, and one of them was the configurations pairs and something related to this. And the other one was the paradoxical groups. Now I define a paradoxical action, and after that paradoxical group. Let G act on a state X from left. By this I mean there is a function from G times X to X with this property that the identity element of G, X is X itself for every X in X, and G HX is GHX. It means that there is a homomorphism from G to the set of bijections from X to X, and this function is a homomorphism. There is a homomorphism from G to S of X. So let it is it's an action of G over X, for example, from left. We say that this action is paradoxical if X has a partition like this, it's the disjoint union of AI, I from 1 to n, J from 1 to m of Bj. They cover the whole X and they are disjoint. And at the same time, I need to make this condition. GIAI also cover the whole X, and as well these are disjoint sets, I from 1 to n, and HJ, BJ, J from 1 to m for some set of elements Gi and Hj. So for some Hj and Gi. In this case, we say that this action is paradoxical. And we say that a group G is paradoxical if this action is paradoxical. The action of G over itself from left is paradoxical. Okay, we have already seen a paradoxical decomposition for F2. As you remember, I said that F2 is omega A, omega B, omega A minus 1, omega B minus 1 plus identity. And we see that it is omega A omega A minus 1, omega B, and B omega B minus 1. And so it's a paradoxical decomposition. And as you see, there is element here which make some problems for the definition of us. And for this, let me rewrite the definition of paradoxical decomposition of a group. We say that G is paradoxical if I just want to rewrite this. G is AI, Bj, and disjoint union of GI-AI and disjoint union of HJ-BJ for some GIs and HJs. But there is a theorem that you can find it in many papers. For example, one of my papers in Belgian Math Society, Bulletin of the Belgian, that it's not necessarily need to, these two don't need to be disjoint in general. It can be a normal union, not necessarily the disjoint union, but they must cover the whole of G. G from 1 to n, and this one I from 1 to n, for example. N. And they need not necessarily to cover the whole of G. So it is enough to say G has some disjoint subsets with this property, and they must cover the whole of G. So for paradoxicality of G, it is enough to have some disjoint subsets. I emphasize to this disjointness. They must be disjoint, but they must cover the whole of G, and it's enough. You can prove that this condition is, again, equivalent to the condition of existing of a paradoxical decomposition. I call this decomposition a complete paradoxical decomposition, but they are not complete, and it's not important. You can prove that they are the same, and a number here is very important for us. We say that this number I from 1 to n, and this is j from 1 to m. The number m plus n is important for us. We call this number the Tarski number of this decomposition. M plus n in this decomposition is the Tarski number of that. And the least possible number with this property, the minimum number of this, mn, m plus n, where it is a Tarski number of paradoxical decomposition for G. This is the Tarski number of the whole group. This is tau of G. This is the notation. And if G admits no paradoxical decomposition, we say that the Tarski number of G is infinity. And the point is that if your paradoxical decomposition is complete or it is not complete, the same upper bound for tau of G is obtained. So in each case, the Tarski number of G is less than m plus n. And with no problem, we can use complete paradoxical decomposition or non-complete paradoxical decompositions. So for F2, you see there are 4 groups in the decomposition, and therefore the tau of G is 4. The tau of G is 4 is less than 4, I say, if G is F2. Tarski number of groups has many properties, and I list them here. Some of them, of course, I don't want to claim that this is complete properties of Tarski numbers, but I try to tell something about Tarski numbers, which are very important for us, and we will use them in next sessions. For example, it is very easy to see that the first property says that for each group, the Tarski number of G is equal or greater than 4. And if you know this, the Tarski number of 2 must be 4, not less than 4. Why this is correct? Because if the Tarski number of G is 3 or less, for example, if it is 3, G must be partitioned into 3 disjoint subsets with this property that one of them is make G by itself and 2 others as well. So it is GA and HB KC. For some G, H, and K belongs to G. And it's impossible because this condition says that A must be the whole of G, and therefore B and C are empty. And it's impossible because we have a partition. So the Tarski number of every group is greater or equal or greater than 4. Another property of Tarski number says that if G is torsion, it means that every element of G has finite order in this case. Then the Tarski number of G is greater than 6 or equal to 6. Therefore, if you have a non-amenable group with Tarski number, which is a non-amenable group, which is torsion, the Tarski number is 4, it's greater than 6. And if it is amenable, the Tarski number is infinity. So anyway, it's greater than 6. Before saying the next property, I remind the definition of Burnside groups. A Burnside group with n generators and exponent m is this group. The group Fn, free non-abelian group on n generators over the normal group generated by m powers of elements of Fn. This group is a torsion group. This group is torsion group. Therefore, the Tarski number of B, n, and m is greater than 6 or equal to. But in general, we don't know it is amenable or not. So if it is amenable, the Tarski number is infinity, and otherwise it's greater than 6 because of being torsion. But we know that for each n greater than 2 or equal to 2, and for each m which is odd and greater than, I think, 566, I hope it's right, the Tarski number of B, m, and n is less than 40. With some characterization. Second property, with this property you mean? Greater than 14? Greater than 14? It's less than 14. No, I don't want to explain it. You can find it in many papers and it's known. result. Okay, for example, there is a paper from, let's say, around amenability of a Silberstein, and you can find them here. I'm not sure about the spelling, but you can find the proof in many papers, in many books, everywhere we want. You can find this condition that every torsion group has Tarski number greater than 6, and if you have time, I will explain it to you. So, in future. So we have this property. I will write this in this case under this condition. An and M is between 6 and 14. And another property says that the Tarski number, the set of Tarski numbers is an infinite set. This one is considered in the paper by Sapir, Golan, and Ershov, and I explain it very briefly, but I refer directly to this paper. The Tarski number of groups by Ershov, Golan, and Sapir. Okay, I will explain it, as I said, very briefly. You say before that I need this theorem that it's very easy, that if G is a group with Tarski number, for example, T, with Tarski number T, then there is a finitely generated subgroup of G. In fact, a T generator subgroup. For example, G1 to GT subgroup of G, which is, if it is H, they have the same Tarski numbers. The Tarski number of H is T as well. And it's not difficult if G is paradoxical and G is disjoint union of A and this joint union of Bj. And these two equalities, Hj Bj, then the group generated by G1 to Gn and H1 to Hn is again a paradoxical decomposition, has paradoxical decomposition. And it is enough to make intersection of AI with H and call it, for example, AI prime. And for BI prime, make the intersection of BI with H. Again, they make a paradoxical decomposition for H, and because G1 to Gn and H1 to Hm are elements of H, you see a paradoxical decomposition. But if you get some empty state, you can remove them. No problem. Anyway, the Tarski number of H is less than T, because M plus N is T. For example, if G is a paradoxical decomposition, has a paradoxical decomposition with T members, I mean that N plus M is T. We see that the Tarski number of H is less than T. On the other hand, we have this property for Tarski number. It says that it is saying that if G has a subgroup H, then the Tarski number of G is equal or less than the Tarski number of H. And keep this in your mind. After looking at this theorem, we see that the Tarski number of H must be T, because this is T, and the Tarski number of H is less than T. On the other hand, it is greater than T, and therefore they must be equal. And it's not difficult to prove. I explain it here. If G is, so we are done here. I just want to explain this theorem. Let G be the subgroup of G. Therefore, G is the disjoint union of elements of in this shape, for example. For some G in a set A, the right cosets, I think it's better, right? The set of right cosets of H, make a partition for G, and if G is a paradoxical group, then you see if H is AI and BJ and so on, like we write it so many times, it is GIAI and it is HJ BJ. Write this I want to write a paradoxical decomposition for G, and after that I will conclude that the Tarski number of G is less than the Tarski number of H. So I'm defining some sets, some partitions for G. Look, where G is in this shape, then we have G here, and because H has this partition, you can write it like this. G, where G? G belongs to this set, and it is AIs, and now if you write AI1 prime to be this set, I'm sorry. And for BI, Bj prime, for example, write this. You will get a paradoxical decomposition for G, and therefore the Tarski number of G is less than the number of pieces in this decomposition, and therefore it is less than the Tarski number of H, because in the first time you could choose this as the least number here, I from 1 to n and j from 1 to m. Therefore, we prove this, and in a similar argumentation, you can prove that also if n is a normal subgroup of G, then the Tarski number of G is also less than the Tarski number of G over n. Okay. Now, let's go into next we are going to speak about another definition for groups. And let G be a discrete group. Again, and A and B be two subsets of G. I write A with this notation, and I say that A is equi-decomposable with B. If A and B have the same number, have some partitions with the same number of pieces like this, A is disjoint union of AI, I from 1 to n, and B is the disjoint union of Bj, Bi, again, I from 1 to n, with the same set of pieces, with same number of pieces, and for some Gi in G, each Ai multiplied by Gi is Bi. In fact, it is an equivalence relation. It's not difficult just taking some intersections and some unions. You see that this is an equivalence relation. So a group G, therefore, I just write a note. G is a paradoxical if and only if there are two disjoints. Again, disjoint subsets of G, sorry, only I make this condition for them, A and B, disjoint subsets of G such that G is equi-decomposable by with A and the same time with B. Now, before going on, I need to remind the definition of Cayley graph. I need it. So let's go to the definition of Cayley graph for a discrete group. Let G be a group. Cayley graphs are very useful, in fact, tool in group theory. Definition of Cayley graph. Let G be a discrete group. And G be a subset of such G. Be a subset of G, which can be a generating set or not. It can be finite or not, every arbitrary subset of G. Then the Cayley graph for G with respect to this subset, which is denoted by this notation, is a graph with vertex set to be the whole of G, and the edge set of this gamma is pairs X and Gx, where G belongs to G. We can also define Cayley graph from the right. And I write it from left, and you can define your Cayley graph from right. Let's see some examples of Cayley graphs. Very simple examples I want to give. For example, if G is the addition group of integers and G is only the identity element, no, the identity element for production, for multiplication, not Z only, addition. So if G is, contains 1 and G is the additive group of integers, and starting with 0, you can go to 1, because adding 0 by 1 give you 1. After that, you can go to 2 and so on. And by -1, adding with 1, you get 0 and so on. It's the simplest example of Cayley graph. And another example, you see, if G is, one of the examples that I gave before was this group, Z2 star Z2, the free product of 3 Z2, which was generated by A, B, and C with this property that A2 and B2 and C2, these relations, these are identity. The Cayley graph, it's something like this, starting with the identity element, multiplying by X, you can get here, by Y, sorry, A, B, C. I use A, B, and for example, multiplying by C, you can get here. And because the order of A, B, C are 2, you have directed set, and I don't write the direction because you have edge from E to A and A to E, and I omit the direction. Again, you have AB, AC, and here BA, BC, and here CA, CB, and so on. This is the Cayley graph of this group. And there is a very famous Cayley graph. This is the Cayley graph of F2. And it is important to observe that if F2 is generated by A and B, then the Cayley graph of F2 is something like this, starting again with the identity element, multiplying by A, get here. By B, for example, you from here, and B minus 1 here, A minus 1 here, and the directions are as I show here. Therefore, you see A2, A3, AB, A, B minus 1, A2, B, A2, B minus 1, and so on. And the same happens here. For example, it is B, A minus 1, BA, and so on. If you look carefully, you can see that this is omega A, and this is the complement of omega A. And you know that if you multiply A minus 1 by omega A, you have the whole other parts of the group. Is omega A minus 1, omega B minus 1, and of course the identity element. I also want to give another example of Cayley graphs to conclude something after that. And it's the Cayley graph of a finite group. Let G be S3, the group of symmetric elements, symmetric group over 3 elements. I mean bijections from a 3 elements group to itself. The Cayley graph of this group is something like this because it's generated by, for example, bond 2 and 2, 3. You see that the Cayley graph, if you start again by identity element, multiplying by 1, 2, you get here. And because the order of 1, 2 is 2, you can go back to identity. After that, multiplying by 2, 3 here, you get 1, 2, 3. Again by 1, 2, you get 1, 3. And by 2, 3, you get here 2, 1, 3, 2. And here you get 2, 3 by multiplying by 1. And because this member has order 2, we can finally go to E again. And these are some, you can write 2 directions or omit it. So there are differences between the Cayley graph of a finite group or of an infinite group. I want to use a nice lemma. It is Koenig's lemma. Saying that if G is a finitely generated group, for example, generating by this finite set, then before I continue, I should mention that if G is a finitely generated group generating by G, for example, the Cayley graph of G with respect to this finite set is a locally finite graph, which is connected also. So in this case, we have this thing as well. If G is finitely generated group generating by this set, then take Cayley graph of G with respect to this G contains array. By array, I mean a path with no repeated vertices. So it contains array which start in a point, at a point, at a vertex, and continues through infinitely many vertices. So what it means that there is a set which is infinite and is a subset of G and so on. An infinite subset of G such that for each I, xi plus 1, xi minus 1 belongs to G. Koenig's lemma says something like this. There is some subset here. And using this lemma, I want to prove something else. Our theorem says that a group G is infinite. Let me correct it. Koenig's lemma says that if G is a finitely generated group which is infinite, just for this property, I give these examples here. So if G is infinite, then there are two subsets of G which are equidecomposable, and one of them is a proper subset of the other. And of course, this direction is also correct. I briefly explained this. For this direction, I need proof, and for the other direction, it's obvious because if G is finite, such subsets exist. Because for finite group, equidecomposable subsets have the same cardinal number. So we just need to prove this direction. If G is infinite, by Koenig's lemma, we have such a subset. Now define Bi, Bk, for example. This is our assumption that G is finite, so I write it here. G1 to G is a finite set. So set this set like this, Bk to be the elements of B, where xj plus 1, j minus 1 is exactly gk. From k in 1 to S. For these numbers, define BK as this. Therefore, it is obvious that B is the disjoint union of these sets, BK, K from 1 to S. Now define AK to be GKAK, GKBK, and you see that the disjoint union of AKs, K from 1 to S, is this set, X1, X2 to up to the end. So it's a proper subset of B. If you call this set A is a proper subset of B because it does not contain X0. X0 is here, but not here. So we have two equidecomposable by definition. You see, AK is GK, BK, and B is the disjoint union of BKs. So we have two equidecomposable subsets, which one of them is a proper subset of the others. Now I can conclude another theorem. This one says that for the previous case, I make the condition of finitely generated for our group. I says that a finitely generated group is finite, is infinite if and only if such a thing, because I wanted to use Koenig's lemma, and Koenig's lemma needs the condition of finitely generated. So I emphasize that here G is finitely generated. But for the arbitrary group, we have this theorem. It says that let G be a arbitrary discrete group, then G is finitely generated, is locally finite. Locally finite. If and only if exactly again thing happen, there are subsets A and B of G with that property that A is equidecomposable with B and A is a proper subset of B. So let's explain it very briefly. If I need to prove both directions, for this direction, let G is locally finite and admits such subsets. Let's see what happened. G is locally finite and there are subsets A and B of G, and there are some elements G1 to Gn and some partitions for A and B like this, A1 to AN, B1 to Bn with the same same number of sets, such that AI is GI BI and A is the disjoint union of AIs and B is the disjoint union of BJs. Okay, now look at this set, and A is a proper subset of B. So there exists an element in B minus A, and look at this group. Let H be the group generated by A1 G1 to Gn and X. This group is a finitely generated group, and the whole group is locally finite. Therefore, H must be finite. And these sets, AI prime defining as the intersection of AI and H, and these sets, Bj prime, the intersection of Bj with H, and A to be the disjoint A prime, disjoint unions of AIs because they make disjoint subsets, AI prime, and B disjoint union of Bj primes, Bi primes, sorry, they have the same index because they have the same number of pieces, right? I instead of, okay? It shows that X doesn't belong to B, but to A, but it belongs to B. So this new sets has the same property. A prime is equi-decomposable with B prime, and A prime is a subset of proper subset of B, and these are subsets of H. Therefore, H cannot be finite, but we say that H is finite, and it's a contradiction. So we have something for locally finite groups, and the other side is not difficult as well. You see, if G admits if sorry, again, I think it needs correction. If G is locally finite, there are not such subsets, and by my assumption, I get a contradiction. Now, let G is not locally finite for the other direction. If G is not locally finite, I write briefly as this. Then there exists a finitely generated subgroup G1 to Gn of G, which is not finite. And it is obvious somehow because in this case, but by the previous theorem, there are some A and B equi-decomposable, and A is a proper subset of B, and therefore these are subsets of H and consequently subsets of G, and it is a contradiction. So we get the result. Okay. If G is locally finite, it's not locally finite, then there are subsets with the property I said. And we prove the theorem completely. Okay. Hello again. I will complete our session today, and let's start with another topic which is important for us, and it is some of the main topics for us. The topic that I'm going to talk about is the topic of configurations. So, what are configurations? Let G be again a discrete group, and let G be a finite ordered subset of elements of G. So G is something like this. I use this notation to explain that this set is an ordered set, G1 to Gn, and E to be a finite partition for G. A finite partition for G, I mean that G is AI, I from 1 to M. We say that an element of the set 1 to M to the n plus 1 is a configuration. C is a corresponding to this pair. I refer to this pair as configuration pair in future with this property. If there exists an element in EC0, you see, C must be something like this, C0, C1 to Cn, because it belongs to this set. There exists X in EC0 such that for each J, Gj, X0 belongs to ECJ. This is the definition of a configuration. The set of all configuration corresponding to this pair is denoted by CON of G and E. I use this many times. And before going on, let's give some examples. Again, I start with very simple example. Let G be the additive group of integers, and G be this set 1 and 2 elements of G, and E be this partition, a 2-element partition, E1 and E2, where E1 is 3 multipliers of the elements of Z, and the other one be E2. This is E1, and E2 be the complement of this set. In other words, 3Z plus 1 and 3Z plus 2. This is a partition for G, and this is an ordered subset of G. I want to write the whole configuration of G and E. Remind the definition. You should have a X and X0 in EC0 and so on. Therefore, it depends on the X0 you choose. If your member is in E1, therefore it is something like 3n. Adding this number with 1, you will go to E2, so it is 1, 2, and adding this number again take you in E2. So you have 1, 2, 2, and for choosing numbers from this set, it depends you choose this here or here. If you choose your number from 3z plus 1, you are in E2. Adding by 1, you are going to E2 again. And adding by 2, you go back to E1. And if you choose your number here, you are in E2. After adding by 1, you are going to E1. And after adding by 2, you are here. So, and nothing else. So configuration of G and E consists of 3 elements. These are the only configurations in the CON of G and E for our example. Now, another example. Let G be F2, the group generated by A and B again. Reduce boards in these 2 elements and the empty board. Set G to be the same set, AB. And for our example, E1 to be omega A, the words starting with A, and the identity element, E2 be omega B and omega B minus 1, and E3 to be only this remains, omega A minus 1. So let's write the configuration corresponding to G and E. CON of G and E consists of this configuration. If you choose your number from E1, the first element must be 1. Adding by A, multiplying by A, you go here again. So we have 1, 1, and multiplying by B, you are going there in E2, and that's it. If you choose your number from E2, it can be started by B or B minus 1. If you start by B, after multiplying by A, you get E1, and after B, you are in B. We are starting by B, so it is 2, 1, 2, okay? And if you choose your number here from B minus 1, it has different kinds of elements. It can be B minus 1 itself, therefore you are in E2. By A, you are in E1, and by B, you are going to E1 again. Another kind, you may be this form, B minus 2, and continuing with another reduced word. B minus 2, you are in E2. By A, we are going to E1, and by B, we are going again here. So we have 2, 1, 2. And another thing, in E2, we can be in this form, B minus 1, A minus 1, and so on. Therefore, we are in E2. By A, we get in E1, and by B, we are in E3. This is another case as well. And I continue it here. If your member is something like this, B minus 1A, and up to the end, some stop case, I don't know. You are in E2. By A, we are going to E1, and by B, we are going to E1, and we have this. So I don't write it again because it's here. And I think it's complete by 3. Let me see. If you start with 3, we are starting by a minus 1 and something else. So if it is a minus 1 itself, you have E3, E1, E2. And the other cases, if you are in E3 and it is a minus 1, b minus 1, for example, and something else, you are in E3. By a, you are going to E2. And by b, you are in E2 again. Okay. And let me see if there is another configuration. A minus 1, b minus 1. It can be a minus 2. So we have this. No, a minus 2. It belongs to E2. And no, I think it's 8. That's it. So this is the set of configurations corresponding to these sets. Let me check it, not to leave something. 1 1 2, 2 1 2, 2 1 1, 2 1 2. Okay, it's repeated. 2 1 1. Okay, I have this. 1 1 2, as I say. 2 1 2, 2 1 1. I'll check it. 2 1 1, 2 1 3. I'm sorry. 3 3 2. I will check it. So let me omit the repeated one. 2 1 1, 2 1 3. Okay. 2 1 2. Yeah, we have this. And for this, 3 2 2. And 3 3 2. Yeah, it's the same. Yeah. Yes, we have also this. So this is the complete set of configurations corresponding to G and E. And that's it. It depends on the x0 you choose from the set. For example, if you find your member from E3, different cases give you different sets. I think I will use this one. Okay. There's something here which is important for us. Look at these members. The set of all x0s that can be choose here. For example, in the first example, in these configurations, x0 can be any element in 3z. So it's an infinite set. And for these two, also we have infinite sets. This set is important. These sets of x0s are important for us. We define x0 of C to be this set. Is C0 intersection with the intersection of Gj minus 1, ECJ, j from 1 to n. And again, we can write xj of C to be Gj x0 of C. These are all elements that can be chosen for the first configuration, for every configuration you are talking about. And these are the elements that appear for the, for example, second, third, and so on. And these are sets that can be infinite, though the set of configurations is finite. CON of G and E is always a finite set. And what is the problem? It's a question that rising by Willis, and the definition of configurations is of Willis and Rosenblatt, and I'm just reporting them. And in 2001, and the question is that is there an infinite group such that for each G configuration pair of elements of for G, every configuration pair for G, if they're infinite group G, these pairs are for G. There exists a finite set, finite group, of course, finite group. For example, F, such that CON of G and E belongs to CON of F. By CON of F, I mean, or other groups, I mean all configurations that can be right for configuration pairs of the group. Is there an infinite group with this property? Because for finite groups, always CON of G is finite, and for infinite group as well, these sets are finite. And the problem is, and the question is, can they be somehow the same for finite groups and infinite groups? And we answer this question negatively, and very soon, after some steps. Another thing that's important for us is that the set of all x0 of C, where C belongs to CON of G and E, is a partition for G. Let me complete it as a note. If G and E is fixed, the set of all configurations, set all of x0 corresponding to the configurations in CON of G and E is a partition for G. It is a partition for G. And it's not difficult to see that C1 is exactly C2 if and only if x0 of C1 has non-empty intersection with x0 of C2. Non-empty. Therefore, it definitely make a partition for group G. And we use this in next session many times. And also for CJ. I can rewrite it here. The set of xj for each j between 0 to n. We have this not only for x0s. And therefore, these are subsets that make a partition for our group. You can see this here for the second example. For example, look at this. Number 1, 2, 3. In the first position, you can see them. It means that the x0 of C's really make a partition for group. And in the second position, you see 1, also 2, and also 3. This again means that they cover whole of G, and the last one as well. You have 2, you have 1, you have 3, so they make a partition. They cover the whole of G, and of course they are disjoint. So there is another very important definition here. To every set of configurations, to every pair, of course, of configuration pairs for each G and E. G is an ordered finite set, and E a finite partition for G. There correspond a finite system of equations defined as follow. And we are going to give another characterization for amenability. I stated this in the first of the talk, but I want to explain it more. This system is this one. The sum of FC, where C belongs to CON of G and E, where C0, the first one is I, is equal to FC, C belongs to CON of G, and this time Cj is I. I is a number between 1 and m, and j is a number between 1 and n. The number of elements of this, and m is the number of elements of our partition. FCs are unknown variables corresponding to each C, and C0 is the first element of a configuration. Cj is the j plus 1 element. So let me write these equations for our example. If G is the addition group, Z plus 1, Z and addition, and for that example, I don't repeat it. I just want to write the configuration equations. The configuration equations, this system is denoted by EQ of G and E. And I want to write the equations for the first example. Look at this. You may look for configurations with 1 in the first position, after that in the second position, and finally the third position. We have here, if I call them C1, C2, and C3, C with capital letter, C2 and C3, we have here, if C1, which has 1 in the first position, is equal to if C3 which have 1 in the second position is equal to the FC2, which has 1 in the third position. This is two equations, of course. And for 2, look for configurations which have 2 in the first position. These are FC2 plus FC3 are equal to, for the second position, it is C1 and C2. And for the last position, for 2, we have only C3. Okay. Let me check it again. For the last position for 2, it's C3 P1. Yeah, right? The first position 2 is F2 and F3. The second is 1 and 2. No, right. Okay, try to find a non-negative solution for these equations. Non-negative solution. You know, this system is a homogeneous system and always have 0 solution, but I want to find non-zero solutions for this. If you look at this system carefully, you see that it is enough to set FC1 to be 1/3, FC2 1/3, and FC3 1/3 again, or one non-negative solution. I write 1/3 because I have a purpose. It's satisfied because FC1 is FC3 is FC2, and we have this solution for the system. Okay, let me give the definition of some solutions for our configurations. I think the time is over. We can stop or continue. Oh, okay. It depends on the audience. Oh, okay. We can finish here and here. If there are any questions, I will ask. Oh, okay. Let me see something that is written here. Let me check it. Some of our audience says that something is repeated here. 213, 213. Okay. I'll check it and write it again tomorrow, maybe, but because it must be very precise. And I'll check it now or tomorrow. Because I need this tomorrow, I will check it and write it. Is there any question?